Okay, good morning. Welcome to Introduction to Robotics. This course is about the fundamentals of robotics. Now, robotics is one of the fastest growing technologies. And if you just look at some of the videos on YouTube, you'll see all kinds of different robots changing every day. What we want to cover in this course are the fundamental tools that will allow you to design these robots, to analyze these robots, to program these robots. Okay? All right, so without too much ado, let's begin with a preview of the kind of things that we're going to be covering in this course. Okay? All right, so the first thing we're going to be studying is what is a robot? Okay? So, we're going to begin with the notion of something called a robotic mechanism. Okay? All right, so let's start with a simple example. Okay, this is about the simplest, non-trivial example of a robot, and we're going to use this repeatedly throughout the course. Okay, so there it is. This is called a two-link planar open chain. Okay. Now, the way this works is we have two links here. 1, 2. These are just rigid bodies. So here's my arm. My arm is a two-link planar open chain. Okay. We have two joints. We have this joint, and we also have this joint. Okay? So that's all it is. And let's assume that this joint is fixed to ground. Okay? So this is, as I said, about the simplest version of a non-trivial robot that you can come up with. So how does this work? Well, a typical robot consists of joints. So here we have two joints. Here's joint 1, joint 2. Okay? And as I said, we have links. Here's link 1, link 2. Okay? Now, if we want this robot to do something useful, okay, it has to be able to pick up things, interact with the environment. So it's going to need something like a hand, right? So let's put a hand over here. Okay. Now in robotics, there's a fancy word for this hand. We call it an end effector. Okay. Wouldn't be my choice, but this name has been around for a while, and that's what we're going to go with. More descriptive terminology might be something like a gripper or a hand. Okay? All right, so typical robot consists of joints, links, and an end effector. Okay. Now, how does this move? Well, it moves by rotating the joints. Okay? So we need something that delivers a force or a torque, okay, to rotate this joint. And typically we have motors attached. Okay, so there are motors attached here. And these motors deliver a torque that rotates the joint. Okay, and we also have sensors. Well, the more precise term is joint encoders, which tell us the readings of the joint angles. Okay? All right, so this is a typical robot mechanism. Now, how many motors do we need for this? Well, we have two joints. Okay? So it would seem like we need two motors. right? And these motors can be actuated independently. Okay. All right, let me give you another example of a robot mechanism. Okay, this also consists of joints and links. Sorry about that. Okay, so here's another robot mechanism. And now this indicates that this joint is fixed to ground. Okay, and so this joint also is fixed to ground. Okay. So again, here we have 3 links, 1, 2, 3. We have 4 joints, 1, 2, 3, 4. Okay. And this is an example of, well, it's a 4-bar. 4-bar linkage. Okay, so a linkage is another word for mechanism. And this is an example of a closed chain. Okay, so we saw the word open chain over there. Okay, so now the question is, why is it called closed? Well, it's closed because we can draw a loop. Okay? So there's a loop inside this mechanism, so it's a closed chain. Okay? All right, so let me ask you a question. So how many motors do we need? Okay? Let me ask the question another way. How many of the joints can be independently driven or independently actuated? Okay? Now, in the case of the open chain, we saw that we have 2 joints. We want a motor at each joint. Okay? Then that allows us to move the chain. Now, in this case, we have 4 joints. Okay? How many of these joints can we actuate independently? Okay? How many joints can be independently actuated? Okay, so actuated might be an unfamiliar term to you. So it just means driven by a motor. Okay, and the answer is. Anybody want to take a shot at this? You just hold up a finger. Is it 1, 2? I'll give you a hint. It's not more than 4. Okay. Yeah, it's 1. It's 1. Okay. Only 1 joint can be driven independently. Well, I mean, consider the following. If we decided to actuate this joint, let's say we wanted to rotate it that way, and at the same time we decided to actuate this joint and rotate it in the opposite direction, okay, this would not be good for the health of the robot, right? It would probably break here. Okay? So clearly, for this mechanism, we can only actuate 1 joint independently. Okay? All right, so this one you can just figure out intuitively. Okay, let me ask you a question. Another one. So I'm going to draw this fancy mechanism. Okay, so it's a little bit more complicated than the 4-bar linkage. Okay, so you see how it all works? We have a two-link planar open chain here, here, and here. They're all connected to this rigid body by these rotating joints here, pin joints. Okay, so let me ask you the same question. How many joints can be independently actuated? Okay, so can be independently actuated. Okay. All right, so for this, answer is not so clear. Right? You have to think about it. Okay. Anybody want to take a guess? Well, if you guess, it would just be a lucky guess. Okay, so the answer is 3. Okay. All right, so this is what we're going to be covering the first week. We're going to be able to look at these kind of mechanisms and figure out exactly how many joints can be independently actuated. Okay, so that's the notion of mobility or degrees of freedom. Okay, so a mechanism's mobility, okay, or equivalently, degrees of freedom. Okay. All right, so we're going to come up with some very exact formulas, okay, where we can look at a mechanism like that. We can count the number of links, count the number of joints, and come up with the degrees of freedom, okay, or the number of joints that can be independently actuated. Okay, so that's the first topic. The second topic, okay, relates to grasping. Okay. Now, when we grasp an object, we don't think about it, right? Grasp it, right? Grasp it again, right? Grasp it again. We don't think about, my God, where am I going to put my fingers? Should I use 2 fingers, 3 fingers, 4 fingers, right? Unfortunately, a robot has to think about all these things, okay? So sometimes you've seen demonstrations of robots picking up a cup, right? Moving it. And you'll see the robot stare at a cup for a long time, and then it slowly moves, right? So it's thinking. How many fingers should I use? Where should I place the fingers? Okay. So is it better to use 3 fingers? 4 fingers? If I use 3 fingers, is it better to grasp it this way? Or is it better to grasp it this way? Okay. So here the question is, what's the definition of better, right? So one obvious answer is something that's more stable, right? You can grasp it more firmly. Okay? So that's the next notion we're going to cover. And in some sense, that's kind of sort of the opposite of mobility, right? Okay, so it's grasping slash force closure. Okay? All right, so given an object, and we have a robot hand, where should we place the fingers of the hand? Okay, so perhaps we have some hand like that. Okay, so basic questions. Where should we place the fingers? Okay. Where to place the fingers? Okay. More fundamentally, how many fingers? Okay, so we're going to answer these questions. Okay. Ever wonder why we have 5 fingers and not 6 or 4 or 7? Okay. Well, we'll be able to answer some questions about that. Okay, so that's the second topic. third topic we're going to cover. Actually, this is a fourth topic, but it's going to be a segue into the third topic. Okay, something called forward kinematics. So let's go back to our favorite example. Okay, so there's our good friend, the two-link planar open chain again. And here's the gripper. So if we want this robot to do something useful for us, we have to be able to tell the hand, right, where to move. Okay? So we need to understand the relationship between where the hand is and what the joints are. Okay? All right, so let's try to, for this problem, it's simple enough. So I'm going to do a little bit of a calculation here. So here's my XY coordinate frame. Okay. Let me call the coordinates of the center of the hand Px, Py. Okay. Let me call this joint angle theta 1. We're going to be using theta a lot to denote joint angles. And let me call this joint angle theta 2. Now, notice how theta 2 is defined. Okay. Okay, we also need to know the link lengths. So here's link length L1. This is link length L2. Okay. So we want to know the relationship between the joint angles, theta 1, theta 2, and the hand coordinates Px, Py. Okay? All right, so for this example, it's not difficult. Okay? So Px, if you know trigonometry, this is pretty straightforward. L1 cosine theta 1 plus L2 cosine theta 1 plus theta 2. Okay, Py is L1 sine theta 1 plus L2 sine theta 1 plus theta 2. So there it is. Simple trig. Okay, so if you give me the joint values, theta 1, theta 2, theta 1 and theta 2, then I can tell you exactly where the hand is using this equation. Okay? So this is called the forward kinematics. Okay? So this mapping from theta 1, theta 2 to the hand coordinates, Px, Py, okay? We're going to call this forward kinematic map, or more simply, just the forward kinematics. Okay, so this is the forward kinematic mapping. Okay. All right. So clearly, this is pretty fundamental. Okay, if we want the robot to perform useful tasks. Okay, so this is a simple manipulator. Let's look at a more realistic manipulator. Okay, so now I get to show off my drawing skills. Okay, do a little erasing here. Okay. All right. So for me, this is not bad. So here's another example of a robot. Okay, this one has 6 joints. So here's joint 1. We'll call that theta 1. This is theta 2. Okay. That's theta 3. Okay. Theta 4. Theta 5. And finally, theta 6. Okay. All right, so we need reference frames. We need a fixed frame. So let's say our fixed frame is here. And let's say we have a reference frame attached to the gripper. So let's draw something arbitrary here. OK, so there's my hand reference frame. OK, so I can call the coordinates for the center of this hand reference frame, px, py, pz. Okay. So now let's ask the question, what's the relationship between the thetas and px, py, pz? Okay. That would be the forward kinematics. Okay. But wait, there's more, right? Now, this hand can be oriented this way, can be oriented this way. It can assume different orientations. Okay? So just knowing px, py, and pz is not enough. We need to be able to describe the orientation of the hand. Okay? So what is the orientation of this reference frame? Okay? To describe the forward kinematics, we need a mapping from the joint values, theta 1 up to theta 6, to that, obviously. And we also need some information about the orientation, right? So, and orientation of the hand reference frame. Okay, so before we can talk about the forward kinematics, what we need to do first, if we want to discuss more general robots, is we need to understand how to describe the orientation of a reference frame. Okay, so that's the next topic. Actually, that's the third topic that's going to come before forward kinematics. Okay, so orientations and rigid body motions. Okay. Okay. So orientations, rigid body motions, and then we'll talk about forward kinematics. Then the next logical thing to discuss is the opposite of the forward kinematics, or the inverse kinematics. Okay, so inverse kinematics. Okay, so inverse kinematics is, as I said, the opposite of the forward kinematics. So we can ask this question. Okay. So there's an object located here. I want the robot to pick it up. Okay, so here's some object. Okay, so I need to command the robot to move its hand to this location so that it can pick it up, right? So it probably would look something like that. Okay. All right. So in this case, what we're doing is we're given px, py, the desired location of the hand, and we want to find the joint values, theta 1, theta 2, okay, that will move the robot to the desired location, hand location. Okay, so here's the solution. So we just have to just find the inverse of this, right? All right, is this the only solution? Now, if you think about it a little bit, you'll see that actually there's two ways to pick this up. Okay? We can grasp the object this way. So we call this the elbow down solution for obvious reasons. Or we can grasp it this way. This is the elbow up solution. Okay? So this is a common expression. So here's the elbow down. Here's the elbow up. Okay. So we have more than one solution here. Okay. And this is going to be pretty common. In typical robots, you're going to have inverse kinematics where there are multiple solutions. Okay. In fact, it can get quite extreme. For example, if I have this time a 3-link robot, okay, and I want the gripper to be here, okay, you can see that in this case that there are going to be an infinite number of solutions. Okay. So here we have infinite number of inverse kinematics solutions. Okay? And why is that? Well, it's because we have, in the previous example, we only had 2 joints. In this example, we have 1, 2, 3 joints. We have an extra joint. Okay? So we have redundant joints. Okay. Okay. So we have more joints than necessary. And in this case, we have an infinite number of inverse kinematic solutions. So there the question is, which one should we choose? Okay. So is that an opportunity or is that a hassle? Well, I like to think of it as an opportunity. Right? So how about the human arm? Okay, so if somebody gave me an object, here's the mic, said, grab the mic. Grab it, right? So how many inverse kinematic solutions do I have? Well, I have quite a bit, right? So the human arm is also redundant. We have more joints than necessary. Okay. All right, so we're going to be looking at the inverse kinematics first of non-redundant robots and then of redundant robots. Okay.